Welcome to our next video in the series on condensed matter theory. In this lecture I want to talk about Wiedermann-Franz law. And Wiedermann-Franz law tells you that there is a ratio or a constant ratio between the thermal conductivity and the electrical conductivity times the temperature of the sample. And that ratio is known as the Lorentz number. The electrical conductivity we described in the video on Ohm's law. And now let's here have a look at the thermal conductivity and then calculate those ratios. When we want to have a thermal current or heat transport, we take a rod of our sample, we put one side on temperature 1, the other side on temperature 2, such that there is a constant temperature gradient in the sample, and that will result in a heat flow. And we can talk about the thermal current, J, and we'll put an index Q to show you that this is the heat current compared to the electron current. And this is minus kappa times the temperature derivative as a function of position, the temperature gradient. The heat transport is given by the electrons. And we assume that an electron travels, then at some point in space it will scatter, let's call this position x0, then it will continue to travel, and it scatters now at position x1, and then it travels again out of the sample, or out of the range of interest. By doing so, we have a distance between the two scattering centers that we call x0, that is given by x1 minus x0, delta. We have a distance, delta x, which is given by x1 minus x0. The time that the electron took to travel from x0 to x1 we will call delta t. And then we have a velocity of the electron during this time, which is given by delta x divided by delta t. We can now have a look at the energy transported by this electron from x0 to x1. And delta E is given by the kinetic energy of the electron that we have at point x0, then it travels to x1. At this point it scatters and therefore its kinetic energy is changed, and the difference in these two kinetic energies is the amount of energy that we transport from this point to that point. So we have the kinetic energy that we have at point x1, and the kinetic energy that you get after a scattering event in the Drude model is a function of the temperature, and it is a function of the temperature, which is a function of position. So we start with the kinetic energy that we have at point x0, and then the amount that is taken out is the energy that we have by the kinetic energy that is a function of the temperature, and the temperature is a function of position. So that is the amount of kinetic energy that is transferred from position 0 to position 1. We can, for a sample where we have a constant heat gradient, look at the change of kinetic energy with respect to temperature multiplied with the change of temperature with respect to x multiplied by the position over which we scatter between two scattering events, and that is equal to dE kinetic energy dt dx times Vx delta t. the heat transport is given by the amount of energy that electron passes times the velocity that this electron has. Because that tells you how fast your energy is transferred from x0 to x1. Well, we can now put in the equation for delta E, and we find minus Vx squared delta T, and then the derivative of the kinetic energy with respect to temperature times the derivative of temperature with respect to position. If we now compare this with the definition of the heat current, we see that the prefactor that we have here is exactly kappa, the thermal conductivity. Now we can put in a few of those equations for the free electron gas, and we know that the derivative of the kinetic energy with respect to temperature is exactly the specific heat, which is valid in general. Then we have the ensemble average of the velocity in the x direction squared. Well, we now have to realize which electrons actually do the heat transport, and the electrons that do the heat transport are those electrons that sit at the Fermi energy, because close to the Fermi energy we can have the scattering. We still assume that temperature is small compared to the Fermi energy. So the average velocity squared is the Fermi velocity squared. Now I'm not looking at the average velocity squared, but only at one of the three components of the velocity squared. So this is 1/3 of the Fermi velocity squared. And then we have to look at the average time at which they travel, which is given by tau, the average time between two collisions. And with that we find that kappa is 1/3 Fermi velocity squared tau times the specific heat. So we now can calculate what the Lorentz number is, kappa divided by sigma t, with kappa equal to 1/3 Vf squared tau Cv, the specific heat from one of our previous videos, by n k Boltzmann squared T divided by 2 EF for the free electron gas. The Fermi energy can be expressed in Fermi velocity, E is 1/2 mv square, and the conductivity from one of our previous videos, E and n E squared tau over m. If we put all those equations in, we will find that the Lorentz number is 1/3 pi square k Boltzmann squared divided by E squared. So perfectly given by fundamental constants. And indeed, when we measure the Lorentz number for different materials, then at low temperatures we find very good agreement between experiment and theory. There is some fluctuation between different metals, but in the end, for the simplicity of our models that we have, we're not doing a bad job. Thank you very much. In the next video I want to talk a little bit about the limitations of the free electron model that we've discussed so far, and then we'll go into the need to make our models more realistic and include the lattice as a periodic potential. And with that we'll get to Bloch and the Bloch waves that we have in a crystal. Thank you very much. Stay healthy.